Welcome back to CS 520. Today I'm going to talk about the Intel 64 architecture. This architecture is known generically as the x86-64, and the Intel 64 is Intel's implementation of that architecture. And the architecture actually originated with one of Intel's competitors, AMD, and is known there as the AMD 64. This implementation was later adopted by Intel. It's important to note this is not the Intel IA64 architecture, which is Intel's other 64-bit architecture for their Itanium processors. And the main goal today is to understand how function calls are supported on this architecture. And the important points to be considered are recursion, how the return address of a function is handled, how the return value from a function is handled, and how do we pass parameters. This kind of detail is necessary in order to understand how to implement garbage collectors, threads, etc. on this particular architecture. As the name implies, it's a 64-bit machine. What does that mean? Well, the machine has 64-bit addresses, and in the CPU, the integer registers are all 64-bit wide. There's actually 16 registers available, integer registers available. There's 8 that sort of have historic background: the RAX, RBX, RCX, RDX, RDI, RSI, the RSP, and the RBP. These registers all existed in the 16-bit and 32-bit versions of this architecture. For the 64-bit architecture, though, they've added 8 registers called R8 through R15. Notice that there's a couple special registers that are set up especially to do function calls. So RSP register is known as the stack pointer. RBP I'll be calling the frame pointer. And the program counter on this machine is known as the RIP, because Intel refers to a program counter as the instruction pointer. It's also important to note that the machine has 80-bit floating point registers. We won't be talking too much about floating point on this architecture, but something to put in the back of your mind, that internally the Intel hardware computes on 80-bit floating point values. And these are stored in an Intel specific non-standard format. And the values are converted to and from IEEE formats when they're read and written to memory. And again, put this in the back of your mind, because occasionally I've been involved in floating point computations where I'm comparing the results computed on Intel machines to results computed on other machines, and it's often I've noticed there's slight differences, and it's because of this property that Intel doesn't compute on the IEEE formats. It has actually a wider format, so it actually keeps more bits of precision out there. So if you have a string of floating point calculations without any stores to memory, it actually might produce, Intel would argue anyways, might produce a better result. And it only gets truncated back to 64 or 32 bits when you store it to memory. And sometimes this can cause slightly different results. Again, Intel would argue that the results are actually better because it kept around more bits while you were doing the calculation. But it's just something to put in the back of your mind if you ever end up doing floating point computations on Intel machines. Okay, there is a rich history here I should explain. I mean, the Intel architecture goes back into the 70s. It was originally a 16-bit architecture back then. And so the nomenclature here is based upon that. Back then, the fundamental unit in the machine, addresses and integer values, were 16 bits wide. And so those were known as words. 8 bits is known as byte. That makes sense. But when you go to these longer versions, you've got to keep that history in mind, that they started with a word. So when they expanded the architecture to 32 bits, they called 32 bits a long. And now that they've expanded it to 64 bits, the 64-bit value from their historic point of view is called a quad word. So we'll be talking about instructions that will have these one character suffixes on them that will define the actual operand type. So B for byte, W for word, again, word is 16 bits, long for 32 bits, and quad word for 64 bits. Now, it's confusing because if we think about the C types, using GCC and most C compilers, I assume, the C type for a byte is a character. For a word is a short. What Intel calls a long, a C programmer would call an int. And what Intel would call a quad word, a C programmer would call a long. So that you can see the confusion there. You just have to keep that straight as you move back and forth between C and assembly language for the Intel. Okay, the key to doing functions is that there's a runtime stack where we can store information about running functions. The stack grows from high address down to low address. So if we look at a program in memory, down at the low address we'll see the actual code stored in memory. Beyond that will be static global data. And that's usually fixed. Most programs, the code is given and compiled, and the static data is specified by the program. And so those are usually fixed areas. When you're doing malloc to dynamically allocate memory, then malloc starts allocating in this area, and the malloc grows down on my diagram, which is, of course, towards higher addresses. So you got to be careful about my diagrams. I'll try to be consistent here, but in this diagram, the low address is towards the top, high addresses are towards the bottom. Malloc is growing, grabbing memory, and growing towards higher addresses. The runtime stack, where we're going to store information about running functions, is in high addresses, up in the higher part of memory, and growing back down towards lower memory. So as we call functions, we'll see information pushed onto the stack, and the stack will grow. As the functions return, the stack will shrink back towards higher addresses. Got to keep this in mind. It will be important from time to time. As I mentioned, there was a register RSP, which is the stack register. It's always pointing to the top of the stack. Okay. Well, we have a term for what we actually put on the stack, and that's the term frame. So the stack contains a collection of frames, one for each active function call. So frames are pushed on the stack. When you call a function, and when the function returns, it'll be popped off the stack. So each frame contains the return address for the function that it represents, that it's storing information for. As we'll see shortly, we may need to save register contents because, again, we only have one set of registers per CPU, but we may have many active functions. So each function has to share that one set of registers. Okay. Each function call will have its own copy of its local variables, and it'll have its own copy of parameters, and it may also use stack space for temporaries. The RBP register points to the top frame on the stack. And let's take a look at a diagram that provides more detail for how that works. Again, the stack here, high address towards the bottom, low address towards the top of the picture. Stack is growing up as we call functions, shrinking back as they return. But if we stop the clock on a particular function that's executing, again, as always, the RSP points to the top of the stack. So that's how we know where the top of the stack is. The RBP points into the middle of the top frame. And the way it works is that the frame pointer, again, I'll call the RBP the frame pointer. The frame pointer points to the old frame pointer. So the frame pointer of the function that was running and called this function, which is now on top of the stack. Its frame pointer is actually saved here. And its frame pointer points back, its saved frame pointer points back to that function's frame. And it's a recursive situation, right? That frame pointer will point back to another frame. So you can think of the frame pointer and the saved frame pointers as building a linked list of all the frames. Okay, the frame pointer points to the middle of the frame. That's the way I think about it anyways, the middle of the frame. And again, it points to the caller's frame pointer. And we'll be addressing these components based upon offsets off of the frame pointer. So the local variables are put at negative offsets. In other words, they're at above, but above in this diagram is at a lower address. So we have to subtract from the address in the frame pointer to get the address of these locals. So when we're writing assembly code, then to get at a local variable, we will write something like this, right? -8 off of the RBP register. So the way that's evaluated is the contents of the RBP register, which is the address of that location, is adjusted by adding this negative offset to it. So it backs up by 8 bytes up into here to get that bottom local. Okay. Notice that all our offsets are 8 because the stack is basically storing quad words because the addresses and integer values are 64 bits, 8 bytes long. Okay. So moving up here, we know the locals are here at negative offsets. Even further up on the stack, towards the top of the stack, there might be temporaries allocated to do the evaluation of the function's code, right? Complicated expressions might require some temporaries to be used if everything won't fit in the register set. Okay. Looking down the other direction, what's underneath where the frame pointer points? Well, a +8 offset is actually the old instruction pointer. So the caller's instruction pointer, where we need to resume execution when the top function returns. And again, we're going to look at some sample code and see how this all works from the code point of view. But that old instruction pointer would be at offset 8 off of the frame pointer. Now it turns out the first 6 parameters are passed in registers. We'll look at the details of that in a moment. But if you have more than 6 parameters, they're going to be in this area on the stack. And again, to address the 7th parameter, it would be 16 off of the RBP. Again, I'm focusing on integer calculations here. I'm not going to talk about floating point. The floating point situation is a little more complicated with how parameters are passed, but let's ignore that. We're just going to talk about integers. And remember, integers, when I say integer, I'm including addresses in that. You know, addresses would be stored in these integer registers, just like integer values. Okay. All right, then underneath all that would be, as I mentioned before, other frames. And this old frame pointer would point back to the top one. It would also have a saved frame pointer there, and that would point back to the frame underneath, and so on. So again, you can think about this as being a big linked list of frames. But they're stacked up in function call order, so they will return in reverse order, of course. That's the key thing. Having that runtime stack is the key thing to supporting recursive functions, because the top one might be one call to a function, and right underneath it, if it's a recursive situation, is a call to the same function but earlier in the recursion. Okay. Well, let's take a look at how parameters are passed. So the first 6 integer parameters are passed in registers. Again, the motivation for this is just to speed up the computation. You know, one of the be talking about this later in the course, but one of the big factors about modern architectures is that the memory is much slower than the CPU. So if you can reduce the number of memory accesses, you can speed up the program. So in the 64-bit architecture, they're passing the first 6 integer parameters in registers, and I've just listed them in order. RDI for the first parameter, RSI for the second, RDX for the third, RCX, R8, and R9. And again, as I mentioned before, if you have more than 6 parameters, integer parameters, then those values would be pushed onto the stack. Okay. One thing is these are not actually mandated by the hardware. The hardware doesn't actually care where you put parameters. It doesn't even really know what the concept of a parameter is. So what we're really talking about in the next few slides, including this current slide, is a set of conventions that software developers have agreed upon that when writing code for the Intel 64 architecture, we're all going to do things in the same way. And when I say writing software, this includes the compilers who write a lot of the assembly language, most of the assembly language in the world today, right? We compile it from higher level programming languages, and the compilers agree on these conventions too. And that allows our code to interoperate when it's when I'm writing my C program, my C compiler compiles it and it links it with a C library. We all being the compiler that I use and the C library developer all are making these same assumptions, for instance, about how integer parameters are going to be passed. So when my code calls a C library routine, it all works. But the hardware doesn't actually care. So there's two sort of steps here. There's the hardware design, and then people look at the hardware design and decide what the software conventions are. And of course, often those two steps go hand in hand. All right, well, another convention is that we're all going to put our integer return value from the function in a particular register, in the RAX register. So again, this is important when you're interfacing with a library that's been produced by another person or by compiled with a different compiler. As long as everyone's following the same rules, everything will work. Okay, one other convention is who's responsible for saving and restoring registers. Because again, as I mentioned before, the various functions that are running are sharing the registers. So if I've got important values in a certain register and I call a function, the question is that register going to be corrupted, written to with a different value while we're away executing this other function? So again, we have a set of conventions. It actually divides the registers into two groups, the caller saved and the callee saved. When the caller saved, what we mean is that the calling function is responsible for saving and restoring the registers. And again, the conventions just list the set of registers. RAX, RCX, RDX, RDI, RSI, and R8, 9, 10, and 11 are all to be saved by the caller. So if the caller needs the old value that was in those registers, if it needs it to be there when it gets back, then it's responsible, the caller is responsible for saving and restoring it. So you would save the value before calling it, and you would restore it after the function you're calling returns to you. And where would you save it? Well, it would probably be in that temp area that I mentioned. Okay, or perhaps you'd allocate a local slot. It's really sort of a fuzzy boundary there, I guess, between whether it's a temp or local. But if I needed to save and restore registers, I would probably put it in there somewhere. Okay. And you'd have to plan for that. You'd have to allocate that in the stack. Well, the other side of the coin is set of registers, RBX, R12, 13, 14, 15, and the stack pointer and the frame pointer. The called function should save and restore those if it uses them. So if the called function is planning to use RBX, it needs to save it upon entry and restore it before return, because the caller is assuming RBX, the value in RBX will be maintained across the function call. So if I need to change it for some reason and I'm the called function, then I need to save it and restore it. And again, these are just conventions. They're designed to try to make computations more efficient. You could set it up that every time you call a function, you save all your registers before you do the call and you restore them after the call. But that, again, would be a lot of memory accesses. This is trying to have your cake and eat it too. We break them into two groups, and then we're hoping everybody has enough registers to do their work, and we don't have to do any saving and restoring. That's the idea. Which, again, saving and restoring touches memory, which is very expensive. Okay. So those are sort of the rules of the game, but I think the best way to figure this out is to look at an actual example of some code. And this code is available to you. This is my example code that's in the CS520 account in the public area. And it's called fact.s, fact.s, because it's just a simple recursive calculation of the factorial function. Okay, and in this code, I have both the main program and then a factorial function itself. And we're going to look at that code, each of those separately in just a second. Just want to mention to you, though, that this assembly code, it's Linux assembler. So it's written in Linux assembler. It's important to note that because there's also a Windows assembler. And the confusing thing is if you go to look at Intel manuals, they tend to be assuming that you're using the Windows assembler. And the Windows assembler, unfortunately, flips these operands backwards. Again, it's just sort of, it's not important. It's just you have to realize what environment you're talking in. Are you talking about the Intel assembler, then the operands will be in one order. If you're talking about the Linux assembler, it would be in another order. So when you're reading the Intel manual, sometimes you have to flip those operands in your mind because we're usually going to be coming at it we're always going to be coming at it from a Linux point of view. So again, just make a note that you got to be careful reading the Intel manuals. Use caution. Okay. Anyways, you can take this program and you can compile it actually with GCC. So you can compile it using GCC. You just give it the file name, and like always, you can use the -o flag to give the executable a name. So I would grab that program when you have a chance and fool around with it. You can compile it and execute it, because the GCC compiler, it understands that Linux assembly assumes that assembly language will be in a file called .s. So when it sees the .s, it doesn't actually run the C compiler. Rather, it runs the Linux assembler to take this assembly language and convert it to object code. Okay. But it produces an executable. Actually, we'll link it with the C library because I'm actually calling printf here, as we'll see in just a second when we look deeper into this code. Okay, so GCC, it will assemble it and then it will link it with the C library. And again, because the library and the compiler and myself, because I wrote this code, all are following these software conventions for the Intel about how the registers are to be used, parameters are to be passed, and so forth. All this code will interoperate. All right. So let's take a deeper look at first the main program here. Let me skip that, I guess. I'm going to write on this myself as we go. That was supposed to be my notes to remind me what to tell you. Let's see if we can zoom in on this. Well, we can, but that's pretty intense, isn't it? Let's see if that's better. We'll try it. So again, I'm looking at the same code. I'm just focused on the main program first. I don't know what this little box is doing down here. I'm not sure this experiment is working very well. You guys can let me know what you think. So you look at the code. First thing to note is that these pound sign is a comment starter. All right, so they're line-oriented comments. Pound sign designates a comment. Next thing to note is that the assembler actually assembles into two streams. It assembles instructions into the text segment. So the text segment is instructions. I don't know why Linux calls the instructions text exactly, but it's been there ever since I've been following Unix systems. And it also has a data segment for data. So the assembler is actually putting stuff together into two different streams of bytes. One byte will be loaded in as data, and one byte will be loaded in as instructions. And the dot text, and we'll see later a dot data, are how I toggle back and forth. So I'm just making sure that I'm in the text segment here. The line 8 is just an efficiency issue that when I write code, I want the functions that I write to start on a clean 8-byte boundary. This just improves the performance. It's not actually required, but it's part of the boilerplate. As you'll see here, there's a bunch of boilerplate at the beginning. I'm going to circle it right here. Hopefully I guess I'm going to make it hard for you to read, aren't I? There's boilerplate at the beginning, and there's boilerplate at the end. And this boilerplate is what all good functions do when they start up, basically. So I do the align 8 to get myself on a clean quad word boundary. The dot global is to tell the linker that this function is something the linker should be able to see. In other words, it's something that's callable from another file. If I leave off the dot global, I'm in effect hiding the code from the other modules that are going to be linked together. If you think about this, this is the exact opposite of C. In C, what do? In C, we use the static keyword to hide globals and functions. And by default, again, I'm writing a few things on the side here with this magnification that gets lost, I guess. But when C, the static keyword allows us to hide globals and functions because the default is to make them visible, right? The default is visible. Whereas in assembly language, we're going to use dot global to make visible. And the default is they are hidden. Okay. But that's what's going on here, is that the dot global is saying this factorial function, I want to make it visible. In this case, my program exists all in one file, so why did I do this? I think I made it factorial global so that I could also debug with the debugger. The debugger also, if it's not global, I think the debugger, you can't initially set a breakpoint there. All right. This is the label defining the entry point. Again, same as the name. And what do all good Intel functions do upon entry? Well, they save the frame pointer because the new function is going to reuse it. So they have to save the frame pointer, and they immediately set up a new frame pointer. So they push the frame pointer on top of the stack, and then they take the stack pointer and they load it into the frame pointer. Notice that again, the operands here are moving left to right. When I do a move, I'm moving the stack pointer, in this case, into the frame pointer. That's what's reversed in the Windows assembler world, and what you'll see reversed in the Intel manuals. This is just boilerplate, because the reverse then is the boilerplate down at the bottom. Okay, I'm always going to undo this when I go to return. Right? That first instruction actually we'll talk about later, but the last two instructions are the boilerplate. I'm going to pop Q from the frame pointer so that I am going to take the frame pointer that I saved before, that I saved up here. I'm going to restore it, and then I'm going to do the return instruction, which actually return actually reestablishes the instruction pointer, the program counter. So this is sort of the setup of a new frame and the tearing down of the frame when I go to return. Let's go back to this instruction and this instruction. So in this case, this code, I needed one local variable. And as I mentioned before, I need to allocate that. How do I allocate space in my frame? Well, I do a subtract. Again, I've written right through it to make it hard for you guys here. I apologize for that. But that's a subtract quad word, 8 bytes from the stack pointer. Let's go back to the picture here. Right, I've just established a new frame here. And now I'm adjusting, I'm subtracting from the stack pointer and moving down here. That's allocating a local. Again, I'm subtracting because I have low addresses at the top of this diagram, higher addresses at the bottom of the diagram. Okay. So by subtracting from the stack pointer, I'm moving it away from the frame pointer and allocating some space in here. All right. And at the bottom of the code, I'm going to do the reverse. I'm going to add to the stack pointer and bring it back down towards a higher address to bring it back in line with the frame pointer before I shut down the function. So again, let's go back and look at that instruction. You know, I'm subtracting 8 from the stack pointer in order to allocate a local variable. And down here before I exit, I have to remember to undo that. So I have to do an add of 8 to the stack pointer. Okay, so that's sort of the setup and the shutdown. What's in between? Well, it's factorial. So the first thing I do is I compare the parameter that's been passed to me. And remember, the first parameter is an RDI. So I'm calling factorial of n. Calling factorial of n. It's going to be passed an RDI. So what I'm doing is I'm doing a compare quad word to see if the 0, if I have a 0 in RDI. In the Linux assembler, the $sign means that the item that follows it is an immediate value. Okay, it's going to be immediately available in the instruction. We'll see that when we look at instruction encoding for this machine in the next lecture, I guess. So I'm just checking to see if I have 0 in the parameter, because that's the base of the recursion. What happens here is that the compare instruction actually updates an internal scratch pad called the flags, internal to the CPU. It's a register, actually. It's a CPU register called flags, and you can think of it as the status register. Status register. So the compare instruction actually compares the two values, and it sets some bits in this register inside the CPU about what the result of that compare is. And then the following instruction, which is jump greater than, tests the bit, the appropriate bit in the flags register to see what the result of the compare is. So jump greater than, it goes to this label, which is down here. .L2 is down here. So if it's not greater than 0, then it's going to fall in here, and we know the answer now. We don't need to recurse. The parameter that passed to us was 0, so I'm just going to return a 1. So I move a quad word, $1, again, immediate constant 1, into the register that we, by the convention, we use for integer return values, RAX. I guess another thing I need to tell you is that when you're writing Linux assembler, you always preface a register name with this %. Okay, that's how they distinguish register names from labels. So I'm moving a quad word because I know that what I want when I'm past the zeros, I want to return 1. So I move the 1 into REX, and I do a jump down here to my exit sequence, which again, what's it going to do? It deallocates the local variable, and then it restores the frame pointer of my caller, and the return instruction restores the frame pointer of the, restores the instruction pointer of the caller. And we're done. So that's the base of the recursion. But if we don't have 0, I'm jumping to label L2, and I need to set up a recursive call. So here's where I need the local variable. Because RDI is going to have to be reused for me to pass a parameter to myself in a recursive call, right? I'm going to have to reuse RDI. I take the current value of RDI and I save it in that local slot I allocated. Again, it's -8. Why is it -8? Let's go back to the diagram. Right, -8 is that bottom local, -8 off the current frame pointer. In my case, I only have one local, right? So it's in that one slot right above the frame pointer. So I'm saving the old RDI before I do a recursive call into there. Then how's factorial work? Well, I want to call myself recursively with 1 less. So I take my parameter RDI and I subtract 1 from it. Again, these are all quad word operations. You can see how Linux handles this. That's another thing the Intel assembler does slightly differently. But here, the type of the operand is just appended to these opcodes. Okay, so I do the subtract Q to subtract 1 from my current parameter value, and then I just call the factorial. So here's the call instruction. What the call instruction does is it takes the current program counter, which has been updated. Remember, this machine has the same kind of fetch execute cycle that we've talked about before. It fetches the instruction, it updates the program counter, then it executes the instruction. So the call instruction, when it's executing, the instruction pointer is actually going to be pointing to the next instruction down here, which in this case is the multiply. And what the call instruction does is it takes that instruction, that program counter value, and pushes it onto the stack. Okay, and sets the instruction pointer to be the address of the factorial function, which is again back up here. Okay, so that when we do a function call, go back to the diagram, right? I'm doing a function call. What am I doing? Maybe I'll draw another picture. Let's do a new picture here. Got to get a piece of paper. Right, I'm running along. Here's the top of stack, and now I want to do a function call. When I do the call instruction itself, it pushes the RIP. Okay, so the call instruction pushes the RIP register. And that's going to be pointing to the next instruction in the caller. Then it sets the instruction pointer to be the first instruction of the new function. And if we think about what does the new function do? Well, what do all Intel functions do first, right? They push the frame pointer. So we get the frame pointer pushed, and we get a new frame pointer established. And you can see how the new stack frame gets built here. And if I have locals, I allocate some locals, which means subtracting from the stack pointer, as we see in the factorial program, and now I have my locals. Okay, when I go to do the return, I'm just going to undo that, right? I'm going to get rid of the locals, and then I'm going to pop the frame pointer back into the frame pointer register, and then I'm going to pop the instruction pointer back in the instruction pointer. That's what the return instruction does, right? So the call pushes, and the return pops. Okay, and that's how frames get constructed and deconstructed. All right, we're pretty much done with this code, I guess. Um, because what happens when we return back from the factorial function? The factorial comes back to us. The answer, remember, the return value from the function is going to be an RAX. So what's the final step of factorial? Well, I need to do a multiply. I need to multiply my parameter, which I stashed in my local slot, which is -8 off of the frame pointer. Multiply that by what was given back to me by the recursive call, which is in RAX. So I do the I multiply Q, so it's an integer. It's really three components here. Integer multiply quad word. And take my parameter times RAX, put the result in RAX. That's how this works. And then I'm done. I fall into the exit code, which is to deallocate my local, pop my frame pointer, and return. Okay. So somehow, for some reason, I did the factorial function first. I meant, I think, to do the main function first. Let's go back now and do the main function. Again, a lot of this is the same, right? It's going to start in the same way. Same boilerplate here at the beginning. In this case, I don't have any local to allocate, so you just see the same boilerplate. Line 8, the dot global for main. In this case, it's the main program. You have to make it available to the linker so that we can actually start execution at main. Okay. Push the caller's frame pointer. Establish a new frame pointer. Notice that there, even before main is called, there's some kind of frame. So I think when the operating system is starting a program execution, there actually is a frame put on there for a piece of stub code that finds the command line arguments, builds argv, argc, and then calls the user main. So there's actually a frame underneath the main. If you want, and we may do this on some of our assignments, is if you think about that linked list of frames, you could actually fool around and write some code to go in and try to count how many frames are on top of the stack at any point in time. I think the last frame, the bottommost frame, will have a 0 in that saved frame pointer slot. So it's a nice clean linked list situation, and you can actually run back through and see how many frames are on top of the stack. And I think you'll find there's an extra frame for this startup code that calls the user main. All right, anyways, there's the same shutdown code that we expect, the pop of the frame pointer and the return instruction, which reestablishes the instruction pointer, which in this case, because it's the main, it'll be back in that stub, that OS stub code, which presumably the next thing after main returns is it sort of shuts down the process and reports a value to the shell that's running the process. Okay, the main program illustrates the data segment. Notice again we have a text segment and we have a data segment. In this case, I have a data segment because essentially I'm going to do a call in assembly language to printf, and it's printf the factorial of 10 is %d \n, and the result of calling fact sub 10. Right, in essence, I'm writing assembly code to do that printf call, okay? And that string, that control string, is allocated. The assembler has a pseudo operation called .string, which allows me just to allocate an ASCII string right in memory. And I can give it a label, so I can refer to it by a label up in the code. And that's all put in the data segment. So it allows me to assembler provides support to keep my data separate from my instruction, which usually is a good thing. Keeps me from stumbling around and executing my data by mistake. Okay, so sort of the boilerplate code is the same. In the middle here now I'm just doing that printf call. The first step is to actually call the factorial of 10. So again, I move the immediate constant 10 into the RDI register, because the RDI register is where I always, by the conventions, put the first parameter. Okay, then I call the factorial code, which we just looked at. Right? It's maybe going to do a bunch of recursive calls. I don't care, right? It's going to come back to me eventually with my answer, factorial of 10. And what do I want to do? Well, I want to take that value and call printf. Printf, notice it has two parameters. It has the address of that string, and then it has the result of the factorial. So I have to set up two parameters. So I take the label for the string, this lc0, .lc0, and I move it into RDI. And again, I'm using the $ notation because it's going to be like an immediate value. That address from the assembler's point of view is a constant. Right? That address is like a constant, so it's going to be available in immediate mode. I move it into RDI. So if I didn't have that $, I'd be talking about the location, the quad word at the location .lco. And I don't want that, right? I want the address of that location. So the $ here is critical. So I'll stop and reflect about that when you have a chance. It's the difference with the $'s there, I'm talking about the address. If the $'s not there, then I'm talking about the quad word at that address. In this case, I want the address. So I say move quad word $.lco into RDI. RDI again is where the first parameter goes. Second instruction is another move quad word to move the result I got from factorial, which is in the RAX register, and move it into the RSI register. Okay, and then I call printf. There you go. Because we're all following the conventions. The fact that printf was written by somebody else and is in the C library, I know everything's going to work. So printf will go do its thing. It'll print out a number. It's a standard out. When it's done, I'm done. I just do the normal shutdown code. Restore the frame pointer, restore the instruction pointer, and we're done. Okay, so that gives you a quick look at the Intel 64 architecture, in particular how we handle, support recursive functions, how we return values from functions, how we pass parameters, how it's all organized around a runtime stack. That's a stack of frames. So let's stop here.